So my name's Hong Ui. Hope you all had a good lunch. Please don't fall asleep. Yeah, okay. Today I'm going to be talking about data science workflows using Microsoft R Server 9. So there's been actually quite a few big changes in R Server since last year, or last time I spoke, which was actually 2 years ago now. First of all, though, how many of you here know about R or use R? How many here have never heard about R at all or know very little? Okay, a few, it's all right. You'll be totally lost. Okay. Hopefully I can do something to make you a bit less lost. Okay. Okay, so what I'll be talking about today, so as you may or may not know, so Microsoft R Server is I guess now distributed with SQL Server 16. That's probably how most of you will have come to know it. Like I said, there's been quite a few big changes to what we've done with R since the beginning of last year. We have a package for machine learning called Microsoft ML, a package for SQL operationalization called SQL R Utils, deploying web APIs using another package. So I'll be talking about all of those and also a bit about maybe putting it all together in a full process using this thing called the Team Data Science process. Okay, so you may have heard of things like CRISP-DM or SAS's SEMA methodology. So I guess this is our contribution in that space. And I'll be sort of showing it off with a little demo, classifying galaxies. This was based on a talk that a colleague of mine gave at the MLADS conference last year. Bonus, you'll get a lot of pretty pictures of galaxies as well. Okay. Okay, so first of all, what is R? Obviously, R is a statistics programming language. So just before I do that, though, maybe a bit of introduction for myself. For those who don't know me, like I said, my name's Hong Ui. This is my second job on the vendor side. So I actually started off with NRMA Insurance in Sydney for several years, and then I went to ANZ. So as I like to say, insurance companies get sort of bad press for screwing over customers or whatever. That wasn't evil enough for me, so I joined ANZ in Melbourne. But this is the 21st century, and big data is where it's at. So then I went off and joined Pivotal, a big data company, to be truly evil, And now here I am at Microsoft. Okay. So anyway, I think I'll spend more of my life complaining about Microsoft products than actually selling them. So that may or may not spill over at some point. Okay. Okay. So languages, like I said, okay, what is R? It's a statistics programming language. A data visualization tool. It's open source, of course. It's a functional programming language. So if you may be perhaps more familiar with F#, so R is probably a bit more like F# than C#. Its syntax, though, is very much C-based. So if you still prefer, braces and lots of funny sort of punctuation marks, R is maybe a bit more familiar to you. Okay. R is a huge community now. When I started using it, probably in the year 2000, or S+ before that, in 96 or thereabouts, it was still mostly an academic language, used for research, used by universities and so on. But these days we have a big community out in industry as well. So lots of big companies are using it for analytics. It's really sort of caught on in a big way. Obviously Microsoft joining it has also helped speed up that process as well. It's taught in many universities. Graduates will be using it. So where 20 years ago they may have been using SAS or GLIM or SPSS, mostly they will know R or Python or whatever. And there's lots of user groups worldwide. Even in Australia, there are R user groups in Sydney and Melbourne, so I've presented at those. And there's an R user group in Brisbane as well, okay? And in Canberra and I think the other capital cities as well, okay? In terms of the ecosystem, we have a CRAN, which is the website where you go to download user-contributed packages. There are now 10,000 packages available there as of, I think, like 2 weeks ago. That number just keeps going up every time someone talks about it. It's not scalable to big data. I don't know why that's there. I didn't do this slide. And yes, basically, when I basically tell people, if you have an analytics problem, there's an R package to solve it for you. Okay? And obviously, it works on all kinds of platforms, Windows, Linux, Mac, Solaris. It might even be available. Yes, I think it's actually someone's ported it to the Raspberry Pi, I think. Okay. In terms of open source R, there are a few challenges, as people who have used it will probably be aware. First of all is that R is limited in terms of its scalability. It requires that all your data fit in memory, which is good for academic problems. In the small data world, like statistics where I came from, a data set might be big if it's got, say, 10,000 rows. In some of the scenarios we're talking about today, you can have 10 billion rows or more, and R is going to be a bit stretched to cope with that. By default, R out of the box is single-threaded, so there's a language and there's the implementation. In practice, there's only one real open source implementation, which is single-threaded. It works everywhere, very stable, but obviously it's not sort of optimized for efficiency or whatever. Okay, there is a lack of commercial support, which is important for some people. The other thing I like to say is, why get something for free when you can pay for it? And there are very complex deployment processes. So, you've got this language, which is sits off in its own ecosystem, has its own sort of quirks and so on, has its own users. We want to deploy that to sort of like a broader corporate ecosystem. Maybe you want to put it make it available to other apps, to other business processes, and this can be a problem. Okay, so I guess what Microsoft is trying to do is solve these problems. So we provide you with peace of mind. So now, if you don't want to get something for free, you can indeed pay for it. We give you a library of optimized algorithms to do machine learning in a multi-threaded and efficient way. I won't be talking so much about that in detail because this is not really a data science conference, but I'll be describing that. I'll be showing you an example of how we use that. It's going to be scalable to big data. We're going to show you also how you can take your models which you fit in R, deploy them into your SQL database or any database, call them as a web API, and so on. Okay, so in particular, those last 2 points, these are, I guess, things that I think we've really improved over the last year. Okay, so yeah, enough about R marketing. First thing I want to talk about is this package called Microsoft ML. Okay, so first of all, has anyone any questions so far? If any questions, just please feel free to interrupt me midway through. Okay, so we have this package called Microsoft ML. Okay, this is, I think, just been released in the last few months. And basically, it's going to be taking this toolkit, which we have internally in Microsoft, which is called TLC, which is basically a world-class library of machine learning algorithms and transformations. And we're going to put an R interface on it. Okay, so it's going to give you sparse, scalable learners, which are used in practice in Microsoft. So they are used by areas like the Bing team, the ads team, to do learning. Okay, they aren't really state of the art. So basically, the TLC team has links to Microsoft research, and when they develop like tweaks to algorithms, they get implemented straight into TLC. Okay, so we are going to be putting an R interface on that, so you'll be able to call these algorithms, these featureizers from within R itself, using an R front end. Okay. So Microsoft ML is in R Server 9 now. Okay. So you can get that right now. That said, it's not a full-blown totality of TLC. So it's TLC is this huge library. We're not sort of like exposing it all immediately. So we don't quite have the resources to do that. But we're sort of like shipping it like a bit at a time. Okay.
Is part of the Microsoft R node which comes up with the Spark cluster?
Sorry.
Is part of the Microsoft R node which comes up with when we deploy the cluster, we get R node. Will it comes up with that?
Well, if you want to use it on Spark, you can deploy it on the Edge node. At the moment, it won't take advantage of Spark yet, but doing multi-node is one of the things that's on the roadmap. Okay. At the moment, this is multi-threaded, so I'll actually talk about that, but not multi-node just yet. Okay, so we have this vision, okay? We want to be the best machine learning R package. Now, I mean, personally, this sounds a little bit arrogant to me, but who knows, you want to have a stretch goal, right? But we have various things in mind. So, for example, we want to make things like featureization simpler. And we have methods to basically do auto-featureization, auto-tuning. You can basically say, if you use something like Caret, the Caret package will let you do things like, automatically not just fit a model, but also tune it to give best performance over a range of various parameters. So it will choose those parameter values for you. So we want to do something similar. There will be a consistent interface, easy operationalization via the rest of Microsoft R as well. Okay, like I said, we believe this can be better. So in particular, we say we are competitive with things like XGBoost. It's going to be scalable by rows and columns. Okay, not just in terms of like fitting to 10 billion rows, but fitting to 1 billion features. So if you work with text data, for example, working with like document term matrices, you can have like your terms can number in the billions, especially when you're dealing with things like Bing search data. So TLC is useful on problems like those. Okay, like I said, faster. It's going to be multi-threaded. Unlike many sort of like native R packages, which are just single-threaded by default. It's going to be multi-core. We're working on multi-node. Okay, and like I said, integrated because at the moment it works on local, in the local compute context. It also works in SQL. Okay, it will work on the Edge node on the cluster. It works on Microsoft Windows. It works on Linux. Anywhere where Microsoft R is available. Okay. Like I said, the key differentiators between us and things like Caret and so on. We are aware of like competitors like XGBoost and H2O, and yeah, we are, I guess, competitive with those in terms of like predictive accuracy in classification, regression, anomaly detection, and so on. Okay, like I said, this package has a certain particular focus on things like text classification because, these are the use cases that Microsoft has put it to. Like I said, used by Bing, Office, and so on. It's used in things like support ticket classification in Microsoft, sentiment analysis. These are all things like examples of like text analysis. Okay. DNNs, so deep neural networks, we allow DNNs with custom topology and GPU acceleration. So we actually have this special domain-specific language called NetSharp to let you specify complex network topologies, including things like convolutional nets, activation functions, and so on. I'll actually be showing that later on for image recognition. Okay, it's GPU accelerated using CUDA. Okay, so this, if you've used neural networks, you'll know that basically you have to use something like GPUs to get decent speed. You're talking about going from maybe weeks of classification time, of training time, down to like hours, whatever. So we support CUDA acceleration, okay? And yeah, like I said, high dimensional data. It will handle features numbering in the billions, okay? This is not something that can easily be done in R right now, okay? So we support various tricks, things like, you know, feature hashing and so on, to handle like data sets of this size in a manageable way. Okay? And we're working on getting things like that into like the rest of Microsoft R as well. Okay? So any questions so far? Okay, all good. So I think there was a question on what is available right now. So these are the algorithms that are in the initial release. So you've got like linear logistic regression, your staples, I guess. FastTree is a boosted decision tree, which is basically like XGBoost, same speed, same accuracy, and I think this is like our go-to recommendation as kind of like your starting point. You don't really know anything about your data, you just want something, use RX FastTree and it will get you something that's kind of like, you know, reasonably accurate. Random forest is another one, which kind of does the same, fills that same purpose, you know, a good sort of like out-of-the-box algorithm that sort of works reasonably well anyway. Okay, RX neural net, GPU accelerated neural nets, like I said, supports complex architectures using the special NetSharp language. So I'll be sort of showing this off in a demo coming up. And finally, like one-class SVM for anomaly detection. Okay, so there's a whole bunch of other algorithms which are not in this initial release, and I think the next update I think will actually be next month, but don't hold me to that. Okay, and in particular, like, you know, SVMs, not just one class, but just regular SVMs, that's going to be in there as well. Okay. Okay, so SQL Server R services, so that's the machine learning part. Now talking about SQL Server in R, I'm guessing that many of you will be are more familiar with maybe SQL than maybe with R. But yeah, so SQL Server 2016 has the ability to run R in the database, or rather, I guess, beside the database. Okay, so giving you, I guess, the speed and performance of SQL, access to all your parallel threading and processing and so on. Okay, scalability, not bound by, you know, memory limits and whatever. Okay, cost effectiveness. This is a big one for me especially because coming from places like banks and insurers, if you want to fit a really complicated machine learning model, often you basically have to dumb it down to get it into your rules engine. By basically allowing you to run R in the database, this sort of sidesteps that whole problem. Okay, you can basically take the code that you write to get predictions, you know, in R. So if you're a data scientist, you fit this model, you've got some code to use this model to get predictions. You can take that code and just transplant it into your database. Okay, and I'll be showing how you might do that as well. Okay. Eliminate data movement across machines. I don't think that is really such a big draw. I think in practice, people will still be fitting models locally, but definitely scoring in database is going to be big. Okay. In terms of the architecture, although I think sometimes we call it in database, but it's really more sort of like beside the database. So in terms of how it works, you can basically either have fit the model in an R process running alongside the database, and the data is shuffled to and from the R process. But there is no data movement back to the client, which I think is probably the more important thing from my point of view. You know, if your data center is in another city and you're using Potato Australian Internet, you're not shuffling 10 gigabytes of data across Telstra's connections or something. Oh, Telstra is a sponsor. Never mind. Okay. In addition to that, we also allow you to fit certain models in the database itself. So things like linear regression, logistic regression, random forests, they will actually be fit natively inside a SQL server, so you don't actually have to spin up a separate process for that. Okay, so it's not always happening beside a database. Sometimes it actually is happening inside the database. Okay, so yeah, I think the main, the big feature that's become available in the last year is that we've really streamlined the process of taking your analytics solutions and putting it into the database. So at the moment, how it works is that as you can take R code and put it into a stored procedure in SQL, and we've really streamlined that procedure, that whole process. You no longer have to be like experienced in T-SQL to generate the stored procedure. You can actually do it all in R. So we have a package to do it all for you in a sense. We also we've exposed new functions to basically take any R object and serialize it into the database. Okay, so you can take this really complicated, funky machine learning model like a neural network or a random forest or whatever, and essentially just serialize it as a var binary max column. Okay, you could do this before, but you had to write a bunch of plumbing code and do some, I guess, byte twiddling. But yeah, we've done it all for you. Okay. So R sub operationalization. So that's talking about R operationalizing R into SQL. This is, I guess, talking about operationalizing R as just a straight web API. So maybe you don't want or you don't need to touch a SQL database. You've got this model and you just want to expose it to consumers via the web, via a REST API. So basically, yes, you can do that using this package, which is called MRS deploy. So again, this is something new over the last year. You can take R, basically turn that into a web service in essentially one line of code. Well, it's probably more like 3 lines of code, but never mind that. You can take this web service and generate a Swagger-based, it will generate a Swagger-based JSON config for you. Generate a Swagger file for you that you can then use to generate code to consume this API. Okay, I don't actually know what Swagger means. These are just buzzwords to me. I'm sure many of you know what Swagger means, though. Okay, deploy anywhere. So, like I said, it is you can deploy. How it works is that you have a machine where you fit your R model. You have a server sitting somewhere that basically spins up an R process on demand. So you talk to the server, it will spin up an R process, load your model, run your script, and return the results via the API. This server can be running Windows, Linux, or whatever. Again, anything that runs Microsoft R. It can be on-prem or in the cloud. Okay? You can do either online scoring or batch scoring. Okay? Again, because this is all using R code to do the scoring, you can score 1 row of data or 1 billion rows of data, however you want. Okay? And it supports all your admin-y type stuff like load balancing, deploying to a grid, all the diagnostic and capacity evaluation tools, of which I know nothing. Okay? And yes, it's reliable, secure, integrates with Azure Active Directory, LDAP, and so on. Okay? Any questions on things I know nothing about? Yeah? So that's actually coming up in a demo, and maybe it'll be a bit simpler, a bit more clearer. Okay. Yeah. So like I said, this is a quick snapshot of the process of how you would do this as a data scientist. So this is me, even though I never actually wear a tie. I don't know who thought it was a good idea to represent a data scientist as the guy wearing a tie. Easy deployment, so you write your code. You know, you fit your model. You know, you've got code to sort of get predictions out of your model or whatever. We have the server. Okay, you have this function called publish service, and you take your model, and you take the code that you use to get predictions, and you pass these to a function called publish service. And publish service will just basically, publish all of those things onto the server for you. Okay? If you are a data scientist, you can then call this other function called get services. Say if you want to test your model or whatever, you know, and essentially call this API and get the results back from within R itself. You know? So this is what I do. For the rest of you, you can just use the API as it was meant to be used, you know, via things like other languages like C#, Java, JavaScript, or whatever, you know, all via a REST API. Okay. So I know about this, and I know a little bit about this, and I know about this. I know nothing about this, but there are many other people at Microsoft who know all about this. Okay, so you can ask them. Yes, from my point of view, this is essentially what it looks like. I build this model. I call this function called publish service, and I pass it my model, and I pass it whatever other bits you need to make use of the model, and that is essentially it. Okay. Some of you may be aware of Shiny. Many of you, I think. So Shiny is an open source package from RStudio, which essentially lets you build web front ends that will call R models. So obviously there's a bit of overlap between Shiny and what I've just described here, but I guess what I would say is the difference is that Shiny is what you use when you want a human to talk to your model. So, you know, it's going to be, you build this front end that is going to be used by people. They will click on buttons or type numbers in or whatever, and you want a result back from your model for that. So MRS deploy, which is what we've got, the name of the package. So what our process is more about is when you want a computer to talk to your model. So you're going to be interfacing this to other apps in your workflow or in your business deployment. You know, so if you want to you know, call this from some kind of batch scoring process or whatever, you know, a computer is going to be talking to this essentially as opposed to a human, and this is what you will use it for. Okay? All good? Okay. So I've talked about a lot of various like components that you can use, you know, to build up a full workflow and so on. Talk a bit more about how you can organize this workflow, I think, a little bit more efficiently. Okay? So, you know, in practice, you can end up writing an alarming amount of code for what you think is quite a simple thing. So, some of you are probably aware, some of you may not be aware, but, you know, there is this thing called a data science life cycle, or an analytics or modeling life cycle. First of all, I guess you have to start with knowing what the problem is, which is can be harder than it looks. You know, you can know a lot about technology, but not know so much about, okay, this guy wants to fit a model for predicting house prices, which is, I think, what was the example was at lunch in our booth, or maybe, you know, predicting NAPLAN scores, which is a project I was involved in last year, or whatever. You have a business problem, and technology people are not necessarily the ones, you know, who will be best placed to answer business problems. Okay, but as a data scientist, you know, you should be able to ask these questions and understand how to attack them. Knowing what the problem is, you then have to get the data to sort of solve the problem. You know, you have to take your data, fit a model to that. That in itself can involve a lot of iteration. So if you know SEMA from SAS, you know, SEMA really concentrates mostly on this. You know, once you've got the data, how do we interrogate it? How do we analyze it? How do we present the results? So SEMA focuses a lot on this data acquisition and understanding bit. Okay, or maybe this model fitting bit as well. You know, once you've got a final model, you then have to deploy it. So do something with it so that other people can use your results. Okay, and I think in practice, this has sometimes been maybe skipped over a lot. I think especially in large companies where you may have your analytics department that just focuses on building these models, and they're using SAS or whatever, and they've got this great model, and now how do you use it? Well, they'll write out this document, and you're like, that's someone else's problem. We've got this great model, and here's this equation, which is maybe like 10 lines long. Go and figure out how to implement that. I think we're trying to, in Microsoft, I think we're trying to overcome this a bit, so maybe make the analytics more integrated into the overall process. Okay? So, like I said, methodologies like CRISP-DM are other people's attempts to try and systematize how you would attack this. So we've got this thing called the team data science process, which is our contribution to this area. I think for the most part, I think it's probably mostly like partly common sense or partly the same things as what CRISP-DM will tell you. But I think there's a couple of unique contributions here. So first of all, we talk about maybe getting a standardized project structure. So, maybe if you have if you have an analytics department, maybe you've got someone working on this project A, and they will put their files into a certain structure, and then you have some other team working on project B, and they'll organize their workflow a different way, and so on. And after a while, if you've been doing this for some time, working out what goes where can itself end up being rather confusing. So we say that as much as possible, try to settle on a standardized organization for where all your files go. Separate out your code and your data, so you don't get these things mixed up. You know what has a sort of like long latency, short latency, stuff like that. We talk about using source code management systems like things like Git and so on. Okay, so especially when you have like teams which may be distributed geographically, so a lot of people may be working from home these days, or maybe you have people in different countries. This maybe applies more to Microsoft than to others, but having a single repository with actual management tools like that can help things tremendously. Okay, so you can get more information from GitHub. So if actually open source all of this, you can get more details there. Okay, so just like talking about organization. So I think if you go to XKCD, they give you this tip, never look in someone else's documents folder. And I'm sure we've all been there. You're talking about document 1, document 2, final document A, final document B, that kind of thing. So, if you had a real sort of like versioning methodology, a real source code management system, you don't have to deal with this problem. Okay? Instead, you have this problem. So this is another XKCD on Git. This is Git. It tracks collaborative work on projects through a beautiful distributed graph theory tree model. How do you use it? No idea, So you just memorize these various commands and just type them in. If you get errors, delete everything and start again. I've done this twice on this project. Okay? But yeah, so despite that, I think Git is still going to be an improvement on things like the old way of doing things. Okay? Okay, so any questions on all those various bits and pieces before I go to the demo with lots of pretty pictures?
Yeah, so you talked about integration with version control and tracking. Does MRS Deploy support that kind of integration? Can you use it?
Yes, it does. So there's like a version tag, so you can actually store multiple generations of your models and so on. So I'll actually be showing that as well.
You talked about Microsoft ML. How is it different from Azure ML? Do you get the same set of algorithms from using both of them, or is it different?
Yeah, so they are in fact different. So you can think of it as like you've got this TLC, which is like this big library of algorithms and so on. And Microsoft basically has exposed various interfaces to this internally and externally now. So you could talk to it via I forget what it's called, but we had various programs that you can use to call into TLC. If you use Azure ML, that's another interface on top of TLC. And now Microsoft ML is an R interface for TLC. Okay. So yeah, so classifying data structure with deep neural nets. Okay, so this is actually based on a talk by Andre de Vries at the MLADS conference last year. So this MLADS is actually an internal Microsoft conference where we talk all about you. I mean, where we talk about machine learning. Okay. Yeah. So this is actually using data from the Sloan Digital Sky Survey, which is a big project aimed essentially at classifying everything that you can see in the sky. And by everything that you can see, I mean everything that giant space telescopes can see. And I think they're up to like a billion objects or some ridiculous number now. Okay. So yeah, there's the first pretty picture. Okay, so in galaxies, each galaxy contains something anywhere from 1 billion to 100 trillion stars. They are anywhere from 2 billion to 2 trillion galaxies in the universe. So yeah, shit is big. Okay. Not just big, but very varied. Okay, so here's one example of a galaxy. That's called a Whirlpool galaxy. I got all of these pictures from the Hubble, essentially the Hubble Space Telescope. That's why they're so pretty. Okay. I think in actual fact, a lot of the images that astronomers use are nowhere near this pretty because they're taken in specific, wavelengths, or they zoom in on like small areas of the sky, which can really only be interpreted by experts. But for members of the public, we just want pretty pictures, so they also provide these. Okay, and they call this outreach. Okay, so this is what's called a spiral. Do we have anyone here who's actually an astronomer or knows about astronomy? No? Good. Okay. No one can pull me up on anything. Cool. Okay. But this is a spiral galaxy. Okay. And the name is obvious. This is one of the more famous ones. The structure is immediately obvious as soon as you see it. You have this nucleus. You have the arms that sort of wind around it. This particular one also has a companion galaxy up on the side there. And in fact, if you look closely, that top spiral arm has actually been sort of distorted a bit by the sort of gravitational interactions with that companion. Okay, so that's the Whirlpool galaxy. It's a sort of like a more diffuse spiral with a small nucleus. But you can have different types of spirals as well. So this is another spiral galaxy. You still have the arms, but this time the nucleus is a little bit bigger, so it's much more prominent. Okay. But you can also have what's called a barred spiral galaxy. So this is NGC 1300, and why do we call it a bar? Because, well, we have this thing in the middle. The arms don't just go all the way around to the center. They connect to this bar, this straight line, and that is what's connected to the nucleus in the middle. And in fact, our own Milky Way galaxy is one of these. So our galaxy it's not just a simple spiral, it's actually got a bar in the middle. Okay? But we don't just have like spiral galaxies. Many galaxies are essentially big, featureless spheres or spheroids of stars. These are called elliptical galaxies. So you have a nucleus. So if you were to take measurements, I think you would find that the brightness or the density of stars grows as you get closer to the center. But other than that, essentially they're these ovoids or egg-shaped or spherical, masses of stars. And these can be like some of the oldest and largest galaxies in the universe, things like up to 100 trillion stars or whatever it is. Okay? And then we have some which are just odd, like, we have this galaxy which is called Centaurus A from the ESO. So it's got this sort of band in the middle. And if we go back to these spiral galaxies, we can see we've got these bands of gas which are dark, and they contrast with the stars around them. So this one has a band, but it's also, it seems like it's just got this spheroid shape of the rest of the star. So it's not really a spiral galaxy, but it's not really an elliptical galaxy either. And I think the consensus is that this is actually the result of two galaxies having sort of collided with each other, and one of them was a spiral. So that's why you have that band of gas like surrounding the elliptical galaxy in the middle. Okay. So how do you make sense of all of this? So there was a really smart astronomer called Edwin Hubble, who in fact is who the Hubble telescope is named for. And he came up essentially with this sort of like methodology for classifying all of these galaxies. So you have the ellipticals on one side, and they're called, anywhere from E0 to E7, based on essentially how spherical they are. And basically, as you go down this side, what you find is that these elliptical galaxies can be either really essentially spherical, or they can get sort of like flatter and turn into something more like a disk. And that disk is essentially where an elliptical turns into a spiral galaxy. So you can have spirals, which are very sort of tightly wound with a big nucleus, or you can have spirals which are more loosely wound with a small nucleus, and similarly you have barred spirals as well. Okay? I think Hubble actually sort of hypothesized that all galaxies start off as ellipticals, and then as they age, they sort of like unwind and turn into spirals. But these days, we know it's actually the other way around. So galaxies, if anything, galaxies start off as spirals. As they age, as they collide with other galaxies, they become more amorphous and turn into ellipticals. Okay? So it's called the Hubble tuning fork. And I think that there's also some other sort of like complications. There's actually a more interesting structure in galaxies that this doesn't quite capture. But this is still quite well known and forms the basis, I think, for a lot of classification work. Okay, so yeah, so that's the background in terms of what people are doing now. So, like I mentioned, the data I'm coming from is from this project called the Sloan Digital Sky Survey, and it's imaged like 900,000 galaxies so far, as well as like who knows how many stars. And essentially, it got to the point where there is too much data for professional astronomers to classify. So I think what's interesting also is that SDSS uses SQL to store its data. And in fact, if you go to TechNet, there's a blog post from Joseph Sirosh talking about how they use SQL Server to store, I think, like a trillion images or whatever it is, along with all the catalog information and so on. And there's also like a demo on the Azure Websites site, basically going through how you work with all this data. Okay, so there's some other Microsoft websites talking about this data as well. Okay, so yeah, basically there's too many images for your actual professionals to work with. So what do you do? Okay, well, obviously you get people to do it for nothing. There's this project called the Galaxy Zoo. So how many of you have heard of? Maybe, yep. So you've got some people who have heard of it. It's essentially like a crowdsourcing project where you get members of the public to come in and look at these pictures and classify them for you. So there's this website, they'll give you this picture on the side, and they ask you various questions. You know, is this just smooth and rounded with no sign of a disc? You know, if yes, then how rounded it is, and so on. If no, well, could this be just a disc? And you work through this flow chart or this decision tree, and you'll come up with a it'll come up with a class at the end of it. Okay, so this is familiar. This is like things like code folding or other sort of crowdsourced science projects. Okay. So that's actually been quite successful, I think. So there's been like Galaxy Zoo 1, Galaxy Zoo 2, 3, 4. I think it's up to 4 or 5 now, all you know, using various subsets of the data that they've gathered. Okay. So yeah, how to classify? We've basically gone from professionals, you know, who know what they do, to citizen data scientists who don't know what they do but are given good instructions, you know, to computer vision, and that is totally not ominous at all. Where the computer has absolutely no idea what it's doing, but we hopefully can give it very good instructions. Okay? So yeah, so for this demo, I'm going to be using deep learning to do image recognition. And deep learning is like one of the go-to methods for this problem nowadays, and I think the other one is SVMs. How many of you know about deep learning? Anyone? Oh shit. Oops. Hopefully I won't screw up this explanation too much, but essentially how deep learning works is that it works in layers. You know, each layer will identify various features, I think, at different levels of structure, and the final result will essentially combine all of these layers together. I actually started out using neural networks back in 2000 or whatever it was. At the time, I think statisticians were this is just like non-linear regression, nothing too fancy. That was like 15 or 16 years ago, and a heck of a lot has happened since then. So I don't think that sort of like attitude's quite accurate anymore. Okay. So we have these various layers which are labeled here as like convolutional or rectified linear units or pooling and so on. So what do all of them mean? Okay, and how do we get the result at the end of them? Okay, so I'll just maybe try and explain what each of these labels means. So a convolutional network essentially just means take this bunch of pixels, and we're not just going to look at the entire pixel. You know, we want to find this image. This image might be in the middle, or it might be on the side, or you know, it might be shifted somewhat. We're going to slide a window across this image and try and look for that picture, you know, everywhere within that sliding process. Okay, so that's essentially what convolution means. The ReLU bit is just a fancy way of saying process the output from this. Okay. Pooling basically is a way of making your model more manageable in a sense, because you can think of this as saying, we're taking this image, which is like maybe, 5 by 5, and we're going to turn that into like 25 by 25, whatever it is. Or in this case, 10 by 10. So you can end up with a lot of output from a fairly small amount of input. So pooling is a way to, I guess, reduce the size of your problem. Okay. What typically happens for image recognition is that, you know, you can take the output from a certain set of pixels, and what's really important is like what is the highest level of activation, or what's the brightest bit of this image, of these set of pixels. So rather than saying, you know, we're going to take a 2 by 2 set of pixels, the brightest pixel had a value of 6, so that's what's important, so we just keep that. So we're going to essentially collapse down our starting data and make that smaller just by taking the max of each subset of pixels. Okay? At the end, the fully connected layers essentially is how you choose a label. So we've got all of these layers, and we're going to feed all of them essentially into what's called a fully connected layer at the end, and that is how it takes all of these pre-processed inputs and gets a chosen label at the end. So, you know, for this particular one, we may be talking about classifying this as a car, a truck, or airplane, or whatever. For this demo, we're talking about classifying, was it an elliptical or a spiral or whatever. Okay? Did I screw that up too much? Excellent. Okay. So in terms of the results, I'm kind of skipping over a lot of the details of the modeling, but you know, this is essentially not really a data science conference. The error rate on the training data was about 12%, 12.7%. If I test that on a separate holdout sample, I get 22%. So this is not great, but you know, there's actually a lot of data that I haven't used, which isn't just images. So each galaxy will have like data on like the location, right ascension and declination, essentially the coordinates of this star, of this galaxy in the sky. You know, you'll have data on the spectroscopic properties of this image, which isn't captured here. You'll have data on maybe you know, the characteristics of the camera or the viewing conditions. All of this auxiliary info isn't used here because I just want to focus on the pretty pictures. Okay. So I'm not saying this is like a great example of how you would use this for classifying galaxies, but this is just like an example. Okay. So in terms of the workflow, what I've done is essentially I've taken this, there's this catalog which you can download from the Sloan Digital Sky Survey site. You can actually even download individual image files. So you know, you can download 1 billion JPEG images or whatever it is. In my case, I've only downloaded like 300,000, okay, which took like 9 hours. Fitting the model took much less time than that, okay? And then you fit and refit the model. You export the model to SQL, create a front end which is callable from the web, and actually build a front end itself, okay? So in terms of model fitting, so this is, I guess, where the magic fitting a neural network happens. Okay, we read in the data using this, we call this function called RxNeural-Net from Microsoft ML. Specify the class labels and the pixels. Okay, this is actually reading images directly from disk. So I'm not going to take all of these JPEG images, which are like 10K or whatever, and then deserialize them, decompress them to something which might be a megabyte. You know, each image is 10K, it will sort of decompress to something 10 times the size. Instead, I'm actually reading them directly from disk. So you have access to various transforms, which are part of Microsoft ML. Or actually, they're part of TLC. So this interface here is like a raw TLC call. We are working essentially on putting our front ends to all of these TLC calls as well. Okay. The actual network definition is basically done in this language called NetSharp, which I talked about before. So for example, that says, you know, we have a convolutional layer, convolve whatever with whatever, you know. And there's a full page on MSDN, I think, that talks about how you use this thing. Okay. This thing is going to be GPU accelerated, like I said. On my laptop, fitting this model took about 80 to 90 minutes. I think if I'd done it using just a standard CPU operations, it would have taken like a week or whatever. Okay. So having got this model, okay, I'll fit this model. If I want to export this model to SQL, okay, it's basically, we have this function called RxWriteObject, and you specify the name of the table where you want it to go. You specify the model itself, and you can specify a key and a version number or version ID. Okay, so essentially the table is just a bunch of key value pairs. The key is whatever you want to call it, and the value is going to be this big var binary max column. Okay, and yeah, we also support versioning and whatnot. All clear? Okay. So prediction function simplified. So the actual prediction function, which I might show you later, I think I've got time, should essentially look a bit like this. You take your model, you take the data set where you want to score, you write the image data out to a file, you pre-process it, and then you call this Rx read object. Okay, so sorry. So first of all, we use this open source ImageR package for image processing. So all the SQL operationalization stuff works not just with Microsoft functions, but with any sort of R function as well. Okay. The image data is going to be just deserialized into a file on disk. Okay, we deserialize the model as well, and then we call that Rx predict function. Okay, to get a label out of it. Okay, so this is basically the same. This is the function that I call in R on my workstation. So exporting code to SQL is essentially the same. Oops. I take that whole function and I call the stored procedure class, okay, which generates T-SQL code to create a stored procedure. And then I basically call this register stored procedure function, and that executes the generated code. Okay. So having created a T-SQL procedure, now because I can, I will create a web API to call it. So this is probably a bit more complicated than it really has to be, but this is a demo. So I will call this library called MRS deploy. I log in to whatever R server it is. In this case, in my case, I'm just using everything on my own machine, so it's just on localhost. But you can use you can log into any other host. You can log in via Azure Active Directory as well. So there's a remote login AAD to use AAD credentials. Okay. This is the function here to get the results. Okay. The inputs are going to be essentially the image that you want to send. We send the image to the database, and then we call the stored procedure using this execute stored procedure function. Okay. So that is the function to call the database. We use publish service to take that and copy that to the R server. Okay, so that creates the web service. Okay. And I can generate this Swagger JSON of which I know nothing to generate the API as well. Okay. All very simple. So let's actually see how it works in practice. Okay, so maybe just going through the code first of all. So this is basically the code to download the images. Essentially, it's not that complicated, I don't think. I probably made it a bit more complicated than it has to be. You essentially just call out to this URL. The first URL is to the actual website, which you can't see there. Okay, so that downloads essentially 300,000 images, which takes a long time. Then I do some pre-processing on that, essentially like cropping them to the same size, rotating them, and so on. So there's actually a bit of work to get everything down to a uniform format. So the training model functions, this function here is essentially what you use to train the model. Okay, so this bit there is the same as this thing there, so that and that are pretty much the same. Okay. This is the code to create that stored procedure, and if you want to see the generated stored procedure, I'm using RTVS, by the way. So this is our funky R front end for Visual Studio. If you have used something like, say, PyTools or Visual Studio, this is R-Tools or Visual Studio. It's going to be part of Visual Studio 2017 as well. So this is a stored procedure that I've actually generated. So it's taken my code, which is in the middle. All of that is code that I wrote. And it's wrapped it in a whole bunch of T-SQL statements to generate a stored procedure, okay, with particular inputs and outputs. Okay. So I deploy that, and that was basically generated by this function there. Then I call this deploy model. Okay. And maybe I'll just show you quickly what MRS deploy can do. It actually, you actually have almost full access to the remote R server itself. So if I do remote login, pass it my credentials. You see this remote there? I'm actually logged in to my remote R server, or in this case, my R server on my machine. But this is a completely separate R instance, so I can type in stuff, and I can interact with it as if it was just any other R instance. I have access to various. It's detected that my input, my packages I have available aren't the same as on the local. If I do stuff like I can type in any R commands. This is actually logged in not as my own ID, but as whatever RServe ID that the server has generated. Okay. Anyway, so let's just oops, what's it called again? Pause to switch local session. That's better. Okay, and I can remote log out to get back to my local session. Okay. So I can show you how that, we can see whether or not that works. So let's just log back in. Okay. So I have a whole bunch of files that I want to use. Okay. So this is actually going to call the API. The API is going to call SQL. SQL is going to call my code and get the results and pass them all back up. Sounds probably way too complicated than it has to be, but what the hell. Okay. So let's log out of that. So I've also built a sort of a front end using Shiny to call this API. So let's see how that works. Now, the first thing you will see is this. This is why you should not get back-end devs to build front ends. Okay. So let's just see how that works. So that's one image. This is actually an image from a training data set. Okay, and it's figured out that's a spiral. So that is going to call the API. That's going to call SQL. That's going to call my procedure and come back up again. Okay, so that all works as it's supposed to be. Maybe let's try another galaxy. Okay, so yep, that's an elliptical galaxy. All makes sense. Yep, all good, yeah? So maybe let's try a different type of galaxy. So it's figured out it's a spiral. I don't know how it's figured out it's a spiral, but it has. Okay. And this is the Ignite conference. So let's see an ignited galaxy. So everything works. Well, maybe this particular galaxy doesn't work, but that's not my problem anymore. Okay? Any questions? All good? Okay, so where was I? So packages used. So these are the packages that I've used in this. So, you know, Erevo Scalar, Microsoft ML, whatever. I've also used a bunch of open source packages. Any workflow that you use, you know, locally, essentially will also work in SQL and will also work in an API. So, you know, this thing is actually going to be calling ImageR and dplyr and whatever on the back end. You know, I'm using Shiny, RODBC to access directory, access databases. You saw a little bit of RTVS. Oh yes, and AutoRest. Okay, so let's have a look at what this, what that API might look like if you are an app developer. So let's go to Galaxy Ignite. Okay, oops. CD data. So how many of you have heard of this tool called AutoRest? Nobody? Basically, it's a Microsoft command line tool that will take a Swagger JSON file and generate code for you to call that API. Okay, so that is the Microsoft AutoRest version 0.17, blah blah blah, and you essentially you tell it the name of the JSON file, and you tell it what code, what language you want it to generate the code in. So let's try that. AutoRest, okay, dash code generator, C# dash input Swagger, whatever. Okay. So we go back into here, data output generator. It's created a whole bunch of C# files for me. Okay. I don't know if you can see that. Now I don't know C#, so obviously I didn't write that code. So, but let's see what it might look like. And hopefully this makes sense to someone who knows C#. Okay, so that has taken my API and that has generated code by which you can actually call it. Okay, and AutoRest supports JavaScript, Java, Python, and so on. Okay, so that is probably the last thing I wanted to show you in terms of where was I? Yeah, so some links. So Microsoft R Server, of course, Team Data Science Process, and a whole bunch of sites that will talk about your Digital Sky Survey, Galaxy Zoo, and so on. Okay. Yep. Continue Ignite learning path, blah, blah, blah. Okay, win a Spark After Dark drone, blah, 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 blah. Okay. All good? Any questions? Oh.